All right, so for our next topic, we have a review of the basic chemistry that we're going to need to understand in order to understand the macromolecules that make up the different parts of cells. So we're going to start with the atom. The atom is a building block of a molecule. The atom has basically two different parts. So in the center of the atom, we have the region we call the nucleus. Now this is different than the nucleus of a eukaryotic cell. The nucleus of a eukaryotic cell is a membrane-bound organelle containing DNA. The nucleus of an atom is just the center of the atom. The atomic nucleus contains two subatomic particles, protons, which are positively charged, and neutrons, which carry no charge. Surrounding the nucleus, we have an outer region that holds the subatomic particle called the electron. Now, electrons are negatively charged, and generally, in an atom that has no charge on it, we have equal numbers of protons in the nucleus, which are positively charged, and electrons outside the nucleus, which are negatively charged. So they balance each other out. When we're talking about different types of atoms, we're going to name them by their elements. So an element is a unique form of matter that has specific chemical properties and specific physical properties, which are largely dependent on the number of protons and electrons inside atoms of that specific element. Now, because we're biologists, we can abbreviate this periodic table a whole bunch. Pretty much, we're going to focus on the most common elements in living organisms, which are carbon, symbolized by C, oxygen, abbreviation O, hydrogen, H, and nitrogen, N. So we can find those here on the periodic table. We got carbon, nitrogen, and oxygen. I got hydrogen over here. So those are the elements we really want to pay particular attention to here. Okay, so if you pull up a periodic table or zoom in on that one on the previous slide, I'm going to show you for a second how we're going to read the information it contains. So the chemical symbol is going to be in the center. It's going to be a letter telling us the name of the element. So in this case, we have C for carbon. On top, so in like a superscript, we have a number called your atomic number. Technically, this tells you the number of protons, so the number of positively charged particles inside the inside the atomic nucleus. But because the number of protons and the number of electrons are equivalent when we have an atom that doesn't carry a charge, essentially that atomic number also tells you the number of electrons that that element is going to have in its atoms. Below, we have the mass number. So the mass number is an average, but it's basically the number of protons plus the number of neutrons. We're not really concerned about atomic mass here. We're not really going to be thinking about neutrons. We're really going to be focusing on the electrons. So the one you really want to pay attention to here is that top number, the atomic number. Okay. So once we have the atomic number, we know the number of electrons that that atom is going to have. And then we need to think about how they are positioned. So this is sort of a schematic. This is simplified compared to how you would learn it in an advanced chemistry course, but this is not chemistry. So this simplification is good for us. So we can think of an atom as having that central nucleus and then a series of shells or orbits around it containing the electrons. Now, each of these shells can contain a very specific number of electrons. In this first shell, so this first one, here in red we have the atomic nucleus. Here we have our first shell. The first shell can contain a total of 2 electrons, and then it's full. The next shell, so here's our second shell, can contain a total of 8 electrons, and then it fills up. And every shell after that, this is why this is 2n, 3n, and beyond, can also contain a total of 8 electrons in order to be full. And when a shell is full, we're going to consider that atom to be pretty stable. Okay, so this is called the octet rule because every shell past this first one can hold a total of 8 electrons. Now, as we're looking at a specific element and trying to figure out how many electrons are in the outer shell, which is really what we need to do in order to figure out bonding arrangements. So we're going to take that atomic number. Here we have carbon. So carbon has 6 protons and 6 electrons. We're really tracking the electrons. Then we distribute them across this circle. So in this first shell, we'd have our first 2 electrons. So 2 of those 6 electrons would end up in this first shell. We'd have 4 left. They'd go into the second shell. And then we'd be out of electrons, but we'd have 4 more spaces for electrons in this outer shell if we were talking about carbon. As we go further to this is why we have 2 total, 10 total, 18 total written below. This is telling us that if we filled up this central shell, and if we filled up the central shell, we'd have 2 total electrons. If we filled up the central shell and then the second shell, we'd have 10 total because there'd be 2 here, 8 here. We'd have 8 more here. So if we have 2, 8, and 8, we'd come up to 18, and so on. So that's just another way that you can sort of figure out how many are going to be in this outer shell if you prefer to do the subtraction like that rather than counting from in to out. Okay, so we care about how many electrons are in the outer shell because we're always going to want to have a full outer shell. So for most atoms, we're going to want to have 8 electrons in the outer shell. Now this leads to something called bonding. So we're going to link atoms into larger molecules by creating chemical bonds. And there are 2 types of chemical bonds. We have ionic bonds and we have covalent bonds. In an ionic bond, the way that our 2 atoms are going to come to a stable point with a full outer shell is that one atom is going to take its electrons, it's going to give them away. It's going to give out all the electrons in its outermost shell to another atom. So it's going to lose those electrons and drop down to the next shell, like within it, the next shell closest to the atomic nucleus. The other atom that is gaining those electrons is going to take them in. It's going to put them into its outer shell. So it's going to get a little bigger, right? It's going to fill up its outer shell. So this actually always happens between 2 types of elements. So when we look at a periodic table, each column or group and each row actually means something in terms of physical and chemical properties, which we don't really have to focus on in this course. But ionic bonds are always going to form between metals, which are on the left-hand side, so like the first 2 columns of your periodic table. And then that central bit are transition metals, so potentially those as well. But really, we're thinking about those 2 leftmost columns as our metals, and another atom that is a non-metal. So we're thinking about those columns on the right-hand side. And the reason that's going to happen is that on the left-hand side of our periodic table, we have atoms that have relatively few electrons in their outer shell. And on the right-hand side of our periodic table, we have elements that have more electrons in their outer shell. And what's happening when we have an ionic bond is that we're trying to give away electrons, but like a small number of electrons. And we're trying to gain a small number of electrons over here. Okay, so here in this case, we see that sodium loses its 1 electron in its outer shell, gives it to chlorine, which had 1, 2, 3, 4, 5, 6, 7, needs 8 to be full, right? So needs 8 to be full, takes that 1 from sodium. So here we see this state after we form this ionic bond between sodium and chlorine. Okay, so both of these now have a full outer shell. You can see that here shown by the fact that this outer shell is actually empty, which means that the next shell below that is full. And here we can see that there are 8 electrons in this outer shell for chlorine. And at this point here on the right, we would call these ions. So we would call this a sodium ion and a chloride ion, which just tells us that we've done this sort of trade of electrons. Ions are always charged. And the reason that an ion is charged is that when you lose an electron, you no longer have a balance between the number of protons in the atomic nucleus and electrons in the orbits outside the nucleus. So if an atom loses an electron, it's like those positive charges in the nucleus kind of shine through. So then that atom becomes a positively charged ion. So in that case, that would be our sodium here. Here it was balanced, so it had like no charge, but it loses this electron, which was negatively charged. So now we have that positive charge shining through. And the opposite happens on our chlorine. So in chlorine, this was kind of neutral, no charge here. Even balance between positively charged protons, negatively charged electrons. But when we take on this negatively charged electron from sodium, we now have an extra negative charge. So chloride ion carries a negative charge. Our other type of bonding that we can have are covalent bonds. Now, in a covalent bond, instead of giving away electrons and accepting electrons, we're going to have electrons shared between the atoms participating in the bond. So in this case, we see hydrogen, 2 of them actually, and oxygen. And we can see that when they bond together, here are electrons in white from hydrogen, electrons in red from oxygen. We can see in this final state, in this covalently bonded molecule, in order to have a full outer shell for oxygen, we want 8 in that outer shell. And we've got it after bonding, 1, 2, 3, 4, 5, 6, 7, 8. But we can see that 2 of those electrons are shared with these hydrogens. Now, hydrogen is special because hydrogen actually stays just in that first shell around the atomic nucleus. So it actually doesn't need 8 in the outer shell to be stable. It only needs 2 because that's the rule for our first shell. So we can see that hydrogen is also stable. It has its original electron and it's sharing an electron with oxygen, from oxygen. So that's that red one here. So this is actually a water molecule. And here I'm just showing you how you would do this math, right? So for oxygen, its atomic number is 8, means it has 8 electrons. So we'd have 2 in its innermost shell. That leaves us 6 for this outer shell. 1, 2, 3, 4, 5, 6. It wants 2 more. Hydrogen only has 1 electron. So those are both in that inner shell, 1 electron here, but needs 1 more to fill that shell. And so what we have happen is hydrogen shares its 1 electron with oxygen. When we have 1 bond form here, we now have 7. So we need another hydrogen in order to get that 8th electron for oxygen. So an oxygen shares with 2 hydrogens in order to get an octet in that outer shell. So this forms H2O, or water. Now, there are some special types of covalent bonds. The first one is really kind of just a side note. We can have multiple bonds form between 2 atoms. So like if we had 2 oxygens and they both want to fulfill their octet, right? They want to have a full outer shell. They can actually share 2 of each of their electrons. And then we'd have like 2 lines connecting these 2 oxygens. We'd have a double bond. The more important thing to know for this class is that we also have a covalent bond called a polar covalent bond. Now, polar covalent bonds are important because they're going to create basically weak charges on different parts of the molecule. So here you can see a slight negative charge forming here on, this happens to be a water molecule. So a slight negative charge collecting on the oxygen in the water molecule. and a slight positive charge collecting here on the hydrogen of our water molecule. Now, the reason that this happens is that not all atoms are like the same amount of sticky. So different atoms actually attract electrons different amounts. Now, most of them, as you can see, don't attract them all that much. This is a table of electronegativity. And electronegativity tells us how attracted electrons are going to be to that atomic nucleus. So when we have two atoms that have similar amounts of electronegativity, we don't have to worry about whether an electron will be more attracted to one or the other. But when we have a difference in electronegativity, so here we have oxygen, you can see it's red, so it has pretty high electronegativity. And over here on the left, we have hydrogen in yellow, so it only has medium electronegativity. So there's a significant difference in how attracted electrons are going to be towards oxygen versus hydrogen. Okay, so they're going to be more attracted to oxygen because it's highly electronegative. So because the electrons are more attracted to oxygen, basically what happens is that they spend more time near the oxygen, or we can think of them as being pulled in closer to the oxygen. Now, an electron carries a negative charge. So if a negatively charged electron spends more time near one of the atoms, that atom is going to start carrying a slight negative charge. And the reverse will be true of the atom where that electron is spending less time. That negative charge isn't there anymore, so it's going to end up slightly positively charged. So here we can see on our water molecule, these are all just different pictures of a water molecule. We're ending up with slight positive charges on these hydrogen atoms because the electrons that they're sharing spend a little more time here around the oxygen, which means that the oxygen ends up with a slight negative charge. Polar covalent bonds also allow for molecules to form a different type of bond, and I want to be careful here because when we say bond here, this is not going to form like a permanent bond like a covalent bond. This is going to be a more temporary, a slightly weaker association. But the fact that polar covalent bonds create these slight local charges means that we're also going to have the creation of something called a hydrogen bond. Now, hydrogen bond pretty basically forms from that attraction of the slight negative charges on oxygen with the slight positive charges on hydrogen. So you can think of hydrogen bonds basically as like, kind of like magnets, right? So slight positive charges on hydrogen end up sticking to negative charges in other places. So a hydrogen bond in like a jar of water or a beaker of water or something, it's going to form these dotted lines between the hydrogen and the oxygen in these water molecules. So just to recap about water, so we're going to have polar covalent bonds between oxygen and hydrogen, and we're going to have hydrogen bonds, which are slightly weaker, between hydrogen and oxygen. So these guys aren't sharing electrons in that hydrogen bond, they're just attracted to each other kind of like magnets. Okay, so the fact that we have these polar covalent bonds, we have hydrogen bonds, we have these slight charges accumulating on our hydrogen and our oxygen, means that water is actually going to be really good at dissolving other molecules with charges. So specifically ions, like our salt, our NaCl, our sodium and chloride ions, they have charges. So it means that if you drop some salt in water, those two ions are going to move away from each other because they're going to be attracted to those slight charges on the hydrogen and the oxygen in the water molecules. The same sort of thing is going to happen with other polar molecules. So if you have another molecule that has slight charges on it, we're not going to pull apart the covalent bonds within that molecule, but the different ends of a molecule that carry slight positive or negative charges are going to orient so that their charges basically match up with the slight charges on our water molecules. So our ions and our polar molecules are going to dissolve in water. They're going to mix really well in water because these charges are all interacting. So we're going to call ions and polar molecules hydrophilic. Molecules that don't have polar bonds, that just have non-polar covalent bonds. So covalent bonds, where those electrons are shared pretty equally between the two atoms, are not going to dissolve in water. And actually the fact that they don't have these charges on them means they kind of repel water, because the water is going to want to interact with more other water molecules instead of with that nonpolar compound. So we're going to call these nonpolar covalently bonded molecules hydrophobic. Hydro means water, phobic, like a phobia, water fearing. So also, when we talk about things dissolved in water, we're going to use the word solvent and solute. So water is always going to be our solvent. So things are dissolved in the solvent, which is water. And the particles dissolved in the water we're going to refer to as our solute. So here we have an example of salt, NaCl, in water. So salt, our sodium and chloride ions here are our solute. And here our water molecules are the solvent. And we can see those associations, right? So NaCl is dissolvable in water. Water is a good solvent for this ionic compound. So the positive charges on these hydrogen atoms in water are attracted to the negative charges on our chloride ion, and the negative charges on our oxygen are attracted to the positive charge on sodium. So we can say that sodium chloride, NaCl, dissociates or comes apart, breaks apart in water. Ionic compounds are going to dissociate in water as these hydrogens are attracted to the negative part and the oxygens are attracted to the positive part. Here we see an example of a different type of compound. I'm going to ask you to guess what kind of property this yellow powder here must have that when we put it in to the water, when we push it down with our fingers, it doesn't dissolve in the water.